Hello, this is Rohit Maurya and this is a tutorial video of unit third, which is bending stresses of beam, or say bending stress of beam, into which we deduce the bending equation for beam, into which we considering the section having particular uh, characteristics based on their shape, which can be a rectangular, circular, hollow, triangular, any type of. So we have discussed or solved uh, many parameters according to which, so here it is one problem we're going to discuss to find how it can be used in practical life. So the question is it here 430 by 160 mm I-beam is to be used as a simply supported beam of span 8 meter. As you can see here, if you added up all these distances, you have 8 meter. The web thickness is 10 mm and the flanges are of 15 mm thickness. This is a cross section of the beam where the dimensions of web and the flange width are given, which is 15 mm thickness. The beam carries a uniformly distributed load of 60 kN per meter over the whole span, as you can see here, which already been applied 60 kN per meter over the whole span. Find whether the maximum bending moment stress is within permissible limits of 180 MPa or not. So we need to find the bending stress and check whether it is greater than or less than the value of 180 m, so to deduce whether beam is going to be failed in this particular loading or not. If not, find the width of 12 mm thick cover plate to be welded to each flange for the section to be safe. Also find the length over which the plate should be extended. So what this question is asking was to find the bending stress by excluding the plates. As you see in this diagram, these are plates which having the thickness 12 mm but unknown width and unknown length, which is going to be placed after deducing whether it is going to be fail or not. So first we deduce it is less than or greater than the value of 180, and then we find if we apply these plates, then what is the value of its width and the length we placed into this beam upside down or upper side and downside, so that the bending stress that's generated due to this load can be handled by beam. So let's just move further. We have these parameters given the question. The capital B is a given width of the I section, D is a depth of the I section, small b is a width of the flange, width of the web, and D is a depth of the flange, web. Web is a middle part and flange is a horizontal part. Okay. T is the thickness of the flange, small w is UDL, uniformly distributed load as applied in the beam, and y is the neutral value of the neutral axis from the top or bottom section, bottom flange, or you say, and sigma p is a permissible stress, which is 180. So first we have to find the moment of inertia of this given beam excluding the plate, which is, we already know the formula, which is bd cube minus bd cube upon 12, where bd cube is for total width and depth of the flange part considering as a rectangular beam, and then we excluding the middle rectangular part. If we add this if we add this part and this part, then we have a internal rectangular section which act as a hollow rectangular section. So by excluding the outer dimension into the inner dimension, we have this formula BDQ minus BDQ upon 12, and by reducing the value is in meter to the power of 4, which is 2.601 into 10 to the power minus 4. And then in case of simply supported beam having the UDL of 60 kN, we have the maximum bending moment, which is small w L square by 8, and by putting the value of small w and L, we have the value of bending moment is 4.8 into 10 to the power 8 Newton per mm. Do we put or change the unit of this bending moment because of the calculation can be done in the formula in these two units to be solved, because the all parameters can be placed in one type of unit system. Now move forward. We have a formula of bending coefficient, which is sigma is equal to my upon I. We're putting the value of m, while the value of y is equal to capital D by 2, which is going to be 430 upon 2, so which is 215, and the value of I, moment of inertia, is already there. The value comes as 396.781 Newton per mm square. This is the value of stress, and you can obviously see that the value of sigma is greater than 180, which is far more greater than 180, as you can see. Thus the stress is produced greater than the permissible limit, so we have to have placed the plates. Okay, then we have the maximum bending moment is sigma p. We putting the value of permissible limit by finding the moment of inertia. Moment of inertia is y is equal to, we already know that, 1215, and by solving this we have a maximum bending moment is this 2.17 into 10 to the power 8, where Tp is the thickness of plate. Then the maximum value of y, by including the plate in upper and downward side, top and bottom of the I section, by adding these two plates we have a different y max, which is before is different, but at this condition we have y max is equal to capital D by 2 plus 12 by 2, which is the neutral axis of this, which is 6, and this addition we have a maximum value of y, which is y plus Tp. Y is equal to what? Y is equal to 215 and Tp is equal to 12. Then y max is equal to 227, because from the neutral axis the farther most distance from till the top of the plate is 227 mm. Then we have a different, or say revised, moment of inertia based on the moment value, which is this, due to the load, is m into y max upon sigma p, which is a permissible limit of stress. So this permissible stress limit under this moment having this much of moment of inertia. Again, I am repeating again, we know that beam cannot handle greater than this stress, but load generating this much of moment. So by comparing these two, we need to find the moment of inertia of a section, which is this. But right now how much we have the moment of inertia, which is this, so we have to subtract, okay, these two value and to find the additional value of moment of inertia to be put in terms of these two plates. So we subtract the value and we have a extra moment of inertia which is needed by the plates. So we can easily find the moment of inertia in terms of the formula, because we already know the thickness of the plate. If we assume the width of the plate is B, then we can easily form the formula of bending moment of inertia, which is BD cube upon 12 for rectangular section, and applying the parallel axis theorem, which states that by addition of area into h square, where h square is the neutral axis distance from the plate to the neutral axis of the total I section, which is assuming to be h. So what is the value of h? Which is equal to 215 plus 6, which is reduced here, y plus tp upon 2, which is 221 mm, and we can easily find the value of b here because b is the width of the plate. Then the formula terms in this way, and we have a value of p, which is 294.455 mm. Then let x be the distance from support at which the bending moment reaches the value of maximum bending moment. We already find the maximum bending moment, which is 2.178 into 10 to the power 8. So to find the how much length we can provide by these plates on top and bottom of the beam, we need to find the maximum bending moment which is generated in this beam, and how much length it considered to be any support, either we choose this part or this part. So let's just have x section from this section, this support, and assuming this section having the maximum moment, which is we already calculated here. So let's just put the formula of maximum bending moment at x section in UDL, which gives the formula of this WLX upon 2 minus WX square by 2. We already have the maximum bending moment value here, okay, where small w is equal to 60 kN per meter in terms of Newton per mm square. Newton per mm is this value, and the value of C can be calculated because we form the formula in this polynomial form or 2 degree equation. Then we find the value of C constant, which is mm here. M is equal to mm maximum bending moment, n upon multiplied 2 upon w. The value of C is equal to this, and the value of F is equal to minus L, which is here. I'm just denoting these as a different constants value, okay, to solve it easily, which is minus 8 into 10 to the power 3, and the value of A, because we already used the value of B into the previous notation, so that's why I didn't use B here, okay. That's why I use F in place of B, and by applying the usual standard formula to find the roots of this equation in terms of x, we have a 6.957 meter, and other part is 1.043 meter, okay. So these two values are the exact value where the length is needed. So 1.04, how much it is? 1.043 meter. So we need the length of plates up to 1.4 near where the maximum movement occurred, and the next length where the maximum movement occurred, because we have a two values of x, which is 1.043 and other value is 6.957. so if we add these two, 1.04 meter and 5.92, we have a distance of 6.957 meter from this support. This shows that we have a 2 points in the beam where the maximum bending moment occurred, where the chances of failure can be achieved, okay. Thus the length of the cover plate is required as LP is equal to x minus x2, which is 5.913, which is the middle order of beam, where the bending moment is not, and it is fixed at 1.043 meter distance from each support. Okay, which can be easily seen that the middle part needs the maximum bending moments where the plate is needed, and the rest part is leaved due to less moment generated due to the UDL load. Okay, thank you.